In this lecture, we're going to introduce homology as a functor. To appreciate what that means, we need to say what a functor is. So let's go back and do a quick review of category theory. A category, and we talked about this before, consists of objects and morphisms. It's similar to a set, but instead of calling them the elements of the category, you call them the objects of the category. And a morphism is that for two objects, O1, O2, in your category, so we write it like this, objects of your category, so let's say C is your category, there is a notion of a morphism between two objects. Now, I'm not necessarily saying that given two objects, you always have a morphism between them, but there is a way of defining what it means to be a morphism. Now, a morphism is something that is a lot more abstract. It does not need to be a mapping. But for the purposes that we're going to be seeing, morphisms are going to be mapping. If you're interested, you can, of course, open up a book on category theory and see how they define what a morphism is. Basically, the way they define a morphism is it's something for which you have a law of composition. Just like we composed morphisms together, in the abstract, a morphism is something for which there's a composition law that has to satisfy certain properties. But we're not going to go there because for us, composition would just be composition of functions. So that's what a category is. We also write that F is an element of Hom between O1 and O2. You can say that these are the set of homomorphisms between O1 and O2. This does not mean group homomorphisms. Those are just morphisms in general. So that's the way that we say it. And we mentioned some examples of categories. Some examples of categories. We mentioned the category top. That's the category of topological spaces, where the objects that make up the category of topological spaces and the morphisms between topological spaces are continuous maps. Then we also talk about the category of pointed spaces, top pointed spaces. Maybe you call it P-top, or however, I mean, I'm not sure what the official notation is, but pointed topological spaces. So here are the objects whose objects are of the form x comma p, where x is a topological space. So you can write it like this. It's an object in the category of topological spaces, and p is just some selected base point in x. This comes up very naturally when we talk about coverings, because when we lift paths, there's always that initial condition that makes everything unique. It also comes up when we talk about fundamental group. With a fundamental group, we talk about loops at a certain point. So that's why we talk about pointed spaces as opposed to just topological spaces. So this is the category of topological spaces, of pointed topological spaces, and those are the objects. And a morphism between two pointed spaces satisfies the property that f from x to y is continuous, and it maps the base point to the base point. So with those conditions, you have defined the category of pointed spaces. Another category that one can talk about is the category of groups. This is the category of groups. And another category is A groups. This is the category of abelian groups. The difference between these two categories is the category of groups, you allow all groups. The category of abelian groups, the objects are specifically abelian groups, but the morphisms in both of those categories are just group homomorphisms. So these are just some examples. Now, the nice thing about category theory is category theory allows you to define ideas more abstractly. And I would like to give you an example. So what I would like to talk about this example that would be relevant later on, in fact, it's something called abelianization. So where G, this is going to be some group, and we want to construct this thing called G-ab, which is what we call the abelianization of G. Now, maybe just to give you an idea, so before we write down the definition, this is sort of, you can say maybe the what we want. Let's say that G is the free group of rank 2. This is free of rank 2. As we've remarked, this group is not an abelian group, but if you abelianize it, then you should get a free abelian group of rank 2. So it's essentially the same group, but now the generators commute with each other. And what is this? This is going to be isomorphic to 2 copies of Z, whereas this group is not an abelian group. Now the question is, of course, how does one define abelianization of a group? So I'm going to show you both approaches. There is a explicit approach where you construct it, and then there's a more abstract approach which proceeds in a categorical fashion. So let me show you the concrete way of doing this. This is the concrete approach. So you're going to let H, so G, this is your group, and H, this is going to be the subgroup of G that's going to be generated by all elements of the form AB A inverse B inverse, where AB is in G. Now, just before we go on, this is a very complicated subgroup. When we say generated by all elements of this form, it does not mean, okay, this is like a mistake. H is not the set of all those, I guess, elements. Rather, H is generated by all those elements. In other words, H consists, so elements in H are products of the type AB A inverse B inverse, where AB is in G. So it's an enormous group. It's an absolutely enormous group. So to give you an example, if you have A1, B1, A1 inverse, let's say A2, A1 inverse, B1 inverse, you can multiply that by A2, B2, A2 inverse, B2 inverse, and the product of those two is an H. So H does not just consist of elements of this form, it also allows various products that you can form using those elements. So you can say that H will consist of finite products of elements of this form. So in general, this is a very complicated subgroup. If this, like, there's an infinite number of different combinations you can form, and that alone is not enough, you then have to consider all of the way they can be multiplied together. So like in the most general case, this can be a rather complicated group. Now, of course, if G is a finite group, then there will be a finite number of such possibilities, and then a finite number of different ways you can multiply them together. So like even in a finite group, writing out all of the different possibilities that you can form could be quite a lot. And then here's the way we approach abelianization. The motivation for this is that if G was an abelian group, then these should become trivial, right? Because the A and the B can be interchanged, and then the A and the A inverse cancel, the B and the B inverse cancel. So that's sort of the motivation for why you're doing this, because you want to be able to say that the words of this form should be trivial if the group was to be abelian. And okay, what you do next is, and then you define the abelianization of G in the following way. You would just take G and you would mod out by that subgroup. Now, you can always form the cosets, but you will have to actually show that H is a normal subgroup of G. and then you get the cosets, and then the cosets will form a subgroup. Well, I'm sorry, the cosets will form a group, and the group that they form is the way you define the abelianization of G, because the motivation again is that elements of this form should become trivial in the abelianization. So you're basically keeping the same group, but then you quotient out by things that should be trivial. And you get a new group out of that, and that group that you get out of it is called the abelianization of G. So this is the concrete way of defining abelianization. And this is probably the way you might have seen it in an algebra class, and I'm going to show you the fancy way of defining it. So we can say this is the categorical approach to the abelianization. So what you do is you have to invent a category. So there's a positive and a negative. The positive is this is elegant, it's nice. The negative is this is a lot more abstract. So in a way, one can argue perhaps it's more complicated because it's more abstract. But if you get it, then it is a lot more elegant in the end. So you're going to introduce a category. So you're going to fix some group, and you're going to construct a category. Let's call it C, whose objects will be abelian groups. Let's call them A, together with a group homomorphism. Let's say F from G into A. So this is the part we need to understand. The objects, they're not just abelian groups, but it's abelian group together with the group homomorphism. It's both of them together. So in other words, that an object of C is a pair. It's an abelian group F, where F from G to A is a homomorphism. So we have defined the objects. Now we need to define what a morphism is. So now given two objects, A1, F1, and A2, F2, a morphism between these two objects, so you would say A1, F1 to A2, F2. So you write like an arrow over here. Now here it's a little bit more abstract. It does not necessarily mean a mapping anymore, because these are sets, whereas you're not going to say one function mapped to another function. Let's call it F. So a morphism between these two is a mapping. Well, maybe we should say it's a homomorphism from A1 to A2, so that the diagram commutes. So basically what we're saying is G is our fixed group. We have A1, A1 comes together with a group homomorphism. We have A2, A2 comes equipped with a group homomorphism. And then a morphism between these two objects. So this over here, this is an object. And this over here is another object. And a morphism between two objects is a mapping between A1 and A2 that commutes with this diagram, so that this mapping, this composition will compute with that composition. So you've just defined the category. Now we are being a little bit sloppy here. We did not give you can say the more formal definition of what a category is, but for our purposes that would be good enough. That we've defined the objects, we've defined the morphisms. And now that we have this, here's the way we can define what the abelianization is. We define the abelianization as the initial object in this category. That's how we define the abelianization of a group. Now technically we do have to be a little bit careful, because the initial object is not just a group, it's a group together with a morphism. So even though we're writing down just a group by itself, it comes equipped with a morphism. So what it would mean here is, in other words, so more specifically, it is an object, let's say G_ab, with some mapping, let's call it phi or something, that is initial, so that if A comma F is another object, then there's a unique morphism from the abelianization to this one that makes the diagram commute. So in a way, what we're saying is this, that the universal property of the abelianization is that it is an abelian group. It's an abelian group that you can map the original group into, and it's like the smallest group, the smallest abelian group with that property, which just the saying is that if you have any other abelian group and you have a mapping from G into the abelian group, this is sort of the smallest one, and so there's a unique way to factor everything through the abelianization. So that's what I mean by there's a unique map to the abelianization that will make the diagram commute. Now, of course, there is a question that will come up here is, how do we know this initial object exists? And usually what you do is the construction, the previous construction, is the justification. So the previous construction, where you have that absolutely gigantic subgroup that you quotient out with, that's the justification for why the abelianization exists. But now that you know that it exists, you often do not go back to the original construction, and you rather use this more sophisticated, fancier way of thinking of abelianization. But this, I think, is a nice illustration of how modern mathematics works. And that's why we call this the categorical approach. You can do this all throughout mathematics. Many of the constructions that one sees in mathematics, especially the ones that are very hideous, which are very difficult to write out explicitly, they're often much more elegantly described in some kind of categorical fashion, where you have to develop a category with an appropriate notion of object and morphism, and then you look for the initial or terminal objects within that category, and that will define the construction that you're looking for in a much nicer sort of a way. And when it comes to showing that such a construction exists, you just have to produce one by any means necessary, and then after you know that you have it, from that point on, you can just use the categorical approach from that point on. So that's what a category is. Now we need to move on and talk about what a functor is. So now let us define what a functor is. Here's the definition. Let C1 and C2 be two categories. A functor, and we denote it as capital F, or whatever you want to denote it by, and it's going to look like a mapping. It should look like a function. In fact, it's very similar to what a function is. A function takes elements in one set and it assigns elements in the other set. A functor is going to do the same thing with objects. A functor takes an object in your first category. So we'll write it like this, an object in your first category, and it assigns, we write this as f of the object, it assigns an object in your second category. So at the moment it feels just like a function, but there's one difference. So here's the difference. And furthermore, it assigns morphisms to morphisms. In other words, let's say you have a morphism between two objects. Between two objects in your first category. then you also get a morphism between objects in your other category. So not only does it map an object to an object, it also takes a morphism between those objects and it assigns a new morphism between their images. If you want to write it more fancy, so this is fancy notation, you would say that if F is in the Hom set between O1 and O2, and if you want to decorate this even further, you can even indicate with respect to the first category. But sometimes putting extra decorations actually makes things a lot more confusing. You want to be careful with how much you decorate your notation. But anyway, you take a morphism between those two objects, then F will assign a morphism between the images of those two objects in the other category, C2. So that is what a functor is. So to put it very simple, it's an assignment of objects and morphisms. And then we want the functor to satisfy two properties. And we require that F satisfies two properties. And the two properties are that F preserves the identity, and the other one is that F preserves commutativity, so commutative diagrams. It will become clear what we mean by those two as we look at the examples. When we say the identity, we're referring to the identity morphism. Now, for our purposes, an identity morphism is just going to be the identity mapping. But in more abstract category theory, the identity morphism is not necessarily a mapping anymore. It's defined by some other conditions. It basically, the identity morphism, it's a morphism through which composition is unaffected. But let's not go there. There's no need for us to be more abstract than we need to. We just want to write down sort of like the bare minimum amount of category theory we need in order to appreciate what we're going to be doing next. And it preserves commutative diagrams. Basically is that if you have a commutative diagrams in the first category and then you apply the functor, then you get a commutative diagram in the other category. And as I said, maybe it's not clear what we mean at the moment, but the examples will clarify this. So that's what a functor is. And now I want to show you some examples. I want to show you two examples, and then I'm going to show you the main example of the lecture. So this is an example of a functor. So it turns out that the fundamental group is a functor. So that might come as a surprise, and that's certainly not the way they thought of the fundamental group in the late 1800s. But the modern way, the modern categorical way, is you can interpret it as a type of a functor. So we call it pi1. So pi1 is a functor from the category of pointed spaces, pointed topological spaces, to the category of groups. So what does it do? Well, you give me a pointed space, right? You give me an object. So given x comma p, an object among pointed spaces, pi1 applied to that, right? We talk about the fundamental group of a pointed space. So pi1, right, the functor applied to that, that is now a group, right? The fundamental group, that's now a group. That's now a group. That is now an object among groups. Furthermore, it has to do something with morphisms, because a functor also has to map morphisms to morphisms. Furthermore, if you have a morphism between two pointed spaces, then we get a morphism between their fundamental groups. And that's the morphism. So we actually talked about this morphism before. That's the morphism that we call F star. That's what we call the induced homomorphism on fundamental groups. Now, if you want to, you can, of course, write pi1 applied to F. But notation-wise, that looks pretty bad. So we usually just write F star because this is indicating that you're using the original F, which was the continuous mapping, and you're using it to construct a homomorphism between the fundamental groups. And let's just recall how the induced homomorphism is defined. So you give me a loop, alpha, right? So alpha is a loop in this space. You have to be a little bit careful. It's actually a homotopy class of loops. Alpha is just one representative for that class. So if you give me a loop over here, you can get a loop over there by just composing with F. So if you do F composed with alpha, you get a loop in the other one. And the reason why this works is very simple, that alpha, let me write it like this. Alpha is a map from 0, 1 into X, right? It's a loop. Right? A loop is a mapping from the interval into X, and the endpoints, they both get mapped to P. So this is a closed loop at P. And then you have another mapping into Y, right? The original F is a mapping from X into Y. And then this composition, if you were to do this composition, you do F composed alpha, that will give you a mapping from 0, 1 into Y. So this composition is a loop in Y, and this is a loop at Q because we're assuming that F maps P to Q. So this composition will give you a loop at Q. And there's also this question of showing that this is well defined, that if you have a different representative, if one has a different representative for alpha that's in the same homotopy class, you'll get a different representative here, but it will be homotopic to the other one. So you do have to actually show it's well defined, but that's not a big deal. Now the part that I want to get to is, let us show, and you actually had this as a homework problem, this is a homomorphism between groups. This is now a morphism between two groups. So, but here's what I really want to get to. We claim that pi 1 satisfies the two conditions for being a functor. And those two conditions is that it preserves the identity and it preserves commutative diagrams. So let's go over that part to clarify what we mean by that. So pi 1 preserves identity. What does that mean? That means, let's say we start with a pointed space, we take itself, and we take the identity mapping. And then we apply the fundamental group functor. So now we have the fundamental group of this going to the fundamental group of that. And we're calling this I star. So that's the induced map. The question here is I star equal to the identity? Is the induced mapping, is the induced homomorphism on the identity homomorphism between those two groups? And this is actually very easy to check, because if you choose a loop, what does I star do to alpha? Well, that is equal to, by definition, this is the way the induced map is defined, it's given by composition. It's the identity composed with alpha. But because this is the identity mapping and you're composing it with alpha, that's just alpha again. And so I star takes alpha to alpha. Right? Alpha goes to alpha. And so this is the identity map. It's the identity homomorphism. The next thing we need to talk about is why it preserves commutative diagrams. So pi 1 preserves commutative diagrams. Let's see how that would go. So imagine we have a commutative diagram of pointed spaces. Like this. Let's call this one F, let's call this one G, let's call this one H. So because the diagram commute, it means that H is equal to this composition. And now we're going to apply the fundamental group functor to this diagram. So it basically means you just decorate everything with pi 1 and you just put stars on all of those. But I'll do it separately right over here. So pi 1 of x comma p, it goes to pi 1 y comma q. We're calling this f star. This is pi 1 z comma r. We're calling this g star. And then we have a map going like this, h star. And the question here is, does this diagram commute? Is it true that h star, is that equal to g star composed f star? That's the question. That's what we have to show. That's what we mean that the functor has to preserve commutative diagrams. So this is a diagram of pointed spaces, and the functor, it takes each of these objects and it replaces them by groups. And furthermore, it takes every one of these morphisms between those objects and it replaces them by homomorphisms between those groups. And we want to see, does the diagram still continue to commute? So this is the basically what we have to check. And the way we check this is actually very simple to check, is you just pick an element over here. You pick a representative for a homotopy class, let's say alpha. Okay, so you pick a representative for your homotopy class, and then you have to check whether the composition applied to alpha is the same thing as H star applied to alpha. So let's verify that. So let's see what happens when we do that. So when we take this composition, F, so we have F star composed G star applied to alpha, that would be equal to G star of F star applied to alpha. But then how is F star defined? F star itself is defined by composition. So this is F star of F composed with alpha, right? That's just the induced map, right? The induced map F star on alpha takes you here. The definition of that is through composition. And then G star applied to that, by definition, is G composed with whatever that is. But functions, the composition of functions is associative, so we can rewrite it like this. And G composed F, well, G composed F, right? We've said that's H, right? That's what we're assuming from the very beginning. So that's just equal to H composed alpha. But that's just another way of saying H star applied to alpha. So look at that. When you do this composition and you apply it to a homotopy class, that's the same thing as taking H star and applying it to that homotopy class. So they're equal to each other, and so that verifies the property that we were after. Now let me give you another example of a functor, and it's that abelianization is a functor. We just talked about abelianization a moment ago, but it turns out that abelianization is a functor. So what we mean is that abelianization, you can think of it as a functor from the category of groups to the category of abelian groups. And basically what it does is that if you're given an object, if you're given a group, an object in the category of groups, then G ab is now an object among abelian groups. So that makes sense, but the follow-up question is, how does the abelianization functor act on morphisms? So basically, let's say we have two groups, F. How do we get? So we know that we can abelianize G1, we can abelianize G2, but how do we abelianize the homomorphism? Maybe we call it F star. I mean, if you want to, I guess you can also write F abelianized for the abelianized homomorphism, but let's just write it as F star. How is this defined? So this is the part which is interesting. So let me show you how to do that. So here's how it works. We have G1, and then we have G1 abelianized. And you have to go back to the definition of abelianization. Abelianization, it's the initial object among all abelian groups. So that means that there is a homomorphism from G1 into its abelianization. And this abelian group, it's the smallest among all other abelian groups. It's the initial object. If there's any other abelian group that you can map, you can take a homomorphism from G1 into the abelian group, then there's a unique way to factor it through this one. Then we also do the same thing with G2. With G2, there is a map into its abelianization. And now look at this. We're assuming we have a homomorphism between G1 and G2. So we have a homomorphism over here, F. Now, here's the part which is interesting. If you were to compose F composed with that, however you choose to call that morphism, but if you were to compose these together, right, you compose them together, then you get a map from G1 into G2 abelianized. And notice what you're getting. G1, that's a group. G2 abelianized, that's an abelian group. And this diagonal, it's a homomorphism from G1 into G2 abelianized. But G1 abelianized, that's the initial object of all mappings, of all abelian mappings, abelian morphisms from G1 into an abelian group. This is sort of the smallest one. And so there has to exist a unique group homomorphism that will make this diagram commute from the universal property itself. And that unique morphism that completes that diagram is what we call f star. So we have defined f star in this very categorical kind of a way without even explicitly giving a formula for it. So that's kind of interesting. And I think this will be like a good homework exercise, is verify that abelianization is indeed a functor. So I told you what the first category is, what the second category is, how it maps objects to objects, and furthermore, how it maps morphisms to morphisms. And now it is your task to verify that it preserves the two properties that a functor is supposed to preserve. You have to show it preserves the identity, and furthermore, it also preserves commutative diagrams. So it's not difficult, but it's a good practice problem to really go through this notion of what a functor is and what it's supposed to do. So these are just two introductory examples to a functor, but what we really want to get to is homology. So we're going to talk about how homology is a functor. And this is our main example of a functor. You can say this is the main idea of this lecture. And that is that homology is a functor. So how does this work? Well, here's the way this is set up. Hn, okay, so for each, in fact, for each non-negative integer, Hn is a functor from the category of topological spaces. It's not pointed spaces, because when we work with homology, we're actually computing the homology of a topological space into the category of abelian groups. Homology gives us an abelian group. So what we have to do, well, it's clear what it does with objects. So if X is an object among topological spaces, then Hn of X is an object among abelian groups. So that part is fine. The part that we have to discuss is we have to discuss this induced morphism. So this is what we want to explain. Now, if we have a continuous map between two topological spaces, then how do we define the induced map in homology? So between Hn of X and Hn of Y. So how is that one defined? Well, it's actually going to be defined in a similar way. So this is going to be very similar to pi 1. But there's going to be some complications. What you basically want to say is homology, it consists of cycles. So you're going to pick a cycle in here. So C is going to be a cycle. And F star of C is what you're going to do it by composition. You're going to do F composed with the cycle, and you're going to end up with something over here. The problem, of course, is you should realize that this does not make sense, because a cycle by itself is not a mapping. It is a formal sum of mappings. So that's kind of what we want to do, but it does not exactly work. So it's a little bit more complicated. So what is a cycle? And also, I should say that this is a representative for a cycle. You can talk about a different cycle which is homologous to the first cycle, and you have to show that it's well defined. So there's more things one has to do, but it's very similar. So here's the idea. A cycle, so if C is an n cycle in X, then by definition C is a formal sum of simplices, AK sigma K. The sigmas are mappings from the n simplex into X. The coefficients are integers, and the boundary of C is equal to 0. That's what it means to be a cycle. It means not to have a boundary. So you're picking a representative in the homology class. So you take a homology class, you choose a representative, that's your cycle, and you want to be able to map this cycle. Now, you can't really do it by composition, but you could do composition with each of the simplices. So what you could do, and this will make sense, is the n-dimensional simplex gets mapped into x, and then x gets mapped into y, and then this composition makes sense. Right? Then this composition makes sense. So you then basically want to say, so maybe it's reasonable, so perhaps it's reasonable to say that the induced map applied to this cycle, you should apply this to each of those. So you would have A1 F composed sigma 1 plus AK F composed sigma K, like this. So that's perhaps the reasonable way to do it. You're going to distribute F because you want this to be a homomorphism, so it has to act on each of these separately. And you do this by, you just compose it with those, you get cycles. But then the question becomes, how do you know that this thing that you get is a cycle in Y? So there's things that one has to show. It's a bit harder than the fundamental group. So here's the way we're going to set this up. So let's clear the board. This is sort of like motivation for what we're about to do, but let's clear the board and do this again. So we have a continuous map from X to Y. And in order to define homology, we have to go to the n-dimensional chains. We have to consider a map into n-1 chains. This is our boundary map. And then we have another boundary map that precedes it. And we're going to do this. And the way we get homology, right, the homology would be the kernel mod the image. So you would take the kernel of the boundary map that gives you the cycles, and then you treat two cycles as being homologous if they are the image of a previous chain. Right, so that's how you get homology. And we also need to work with the homology of Y. So we'll set up the same picture down here. Cn-1y, Cn plus 1y. This is boundary map, boundary map. Of course, all of these boundary maps are different, but we use the same notation because they're defined in a very similar way. And now we're going to have induced maps going like this. We'll have an induced map, we'll call it F star. We'll have an induced map F star. Again, these are different maps, but we call them F star because they're being constructed in a very similar way. So how are these being defined? Well, this is the way they're being defined. By definition, the n-dimensional chains, they're formal sum of simplices. So pick a simplex, sigma. So if you pick a simplex over here, you can get a simplex over here by just composition. F composed sigma. So this part makes sense. Okay, so the reason for this is because if sigma is a mapping into X and X is a mapping into Y, that composition, F composed sigma, will give you a simplex in Y. And this is a free abelian group, and the simplices are the generators for it. In order to define what F star does to a chain, it is sufficient to say what F star does on any single simplex. And then F star will then, it's a homomorphism, so that would mean that if you have a formal sum of simplices, F star will distribute on that formal sum, and then you get whatever the image is down here. The exercise here, so this is the exercise. I'm not going to do it. It's not hard, but you have to just go through it. Exercise, this diagram commutes. So you would have to show that if you do, so you have this square, right? You have this square over here. So if you were to do, let's say, del, if you were to, let's say you were to do D like this, you go D composed F star, right? So you go D, then F star. That's the same thing as doing F star and then D. Now these are different Ds and these are different F stars. But the reason why we call this one F star and we call that one F star is because the mapping is defined in a very similar way. This is composition and this is composition. The only difference is this F star is being composed with simplices of one smaller dimension. But other than that, the way the map is being constructed is very similar. So this is the same thing as F star composed with del. And you really have two squares over here. You have the square on the right and the square on the left, and you have to check it for both squares. Okay, so we have this. Now, if we're willing, so if we are willing to accept this result, that these squares commute, then we can define the induced map on homology from the homology of X into the homology of Y. Then we can do that. So I should say that there are some books, I'm not sure why they do that, but instead of calling this F star, they call it F hash. So they call them like this. And then the homology group, and then the induced map on homology is the one that's denoted by F star. I'm not going to make a big deal out of it. We'll just call them F star. We understand which one is which. So we can now define how this works. So here's how you do it. So you're going to pick a homology class of a cycle in Hn of X, and then we define F star of that class to be F star of that class, the class of F star. So maybe this is the reason why they call this by F hash, because then you can kind of tell them apart. Because otherwise it looks funny when the F star is used in the definition itself. But I think we are sophisticated enough that we understand what we're trying to say. So this F star, it's the F star that's coming over here. So the C, this cycle, it's a chain. A cycle is a special type of chain. And the way you get something in the homology of Y is you take that chain, you apply F star, you apply this, the map in the middle, and you end up in the chain over here, and then you take the homology relative to Y of that chain. Now the question, of course, is F star of C a cycle in Y? Because if it's in, you see, if it's in the homology of Y, then it has to be a cycle. So we have to check that it's a cycle. So let's check. So we verify. So let us check. We have to take the boundary of it. Now this is where we're making the assumption that the diagram commutes. That doing this is the same thing as doing that. That would be the same thing. The diagram commutes. And you can actually see why it's called a commutative diagram, because you can sort of like interchange these two. That's why it's called commutative. So this is going to be F star of the boundary of C. So that's F star of 0. It's F star of 0 because we're assuming that C was in the homology class. It's a representative in the homology class of X. So by definition, C is a cycle, so it has no boundary. And then F star of 0 maps 0 to 0. It's a group homomorphism. So that's going to be 0. So thus, F star of C is a cycle in Y. But then the other question comes up is, this is the other question, is F star well defined? Because we're choosing a representative. So say that we have two homology classes that are represented by two different cycles in Hn of X. Is it true? Then these two are in the same homology class in the homology of Y. That's the question. Well, that's what we're going to check. If they're equal, right? So since C, the homology class of C, is equal to the homology class of C prime in Hn of X, it means that their difference is the boundary of something. Let's call it K for some K in, it's an n+1 chain. Right? That's just the definition of what it means for two cycles to be homologous. Okay, so thus we apply F star to this difference. That would be F star of that. And we get from here, right? We apply f star. Now you have to understand that f star is a homomorphism. It's a homomorphism on chains. So that this would be f star of C minus f star of C prime, which is equal to f star of the boundary of K. So from here we get that f star of C minus f star of C prime. And we're going to use the fact that f star commutes with the boundary, so we can interchange these two. So this would be the boundary of f star of K. Now this is a little bit sophisticated because there's different f stars. Like this f star and that f star are technically different, because you can see there's different f stars. We just have to be mathematically mature enough to know which one it's referring to. But anyway, this just follows from the commutative diagram, and this means, so thus, the homology class of C is equal to the homology class of f star of C prime, precisely because their difference is the boundary of a chain of one higher dimension. So therefore, these are the same homology class in the homology of Y. Okay, so we have checked that. The other thing we need to check is, this is the other thing, is f star a group homomorphism? Well, that part is actually easy. I mean, that part is easy. We're not even going to bother to write it down because that's just going to insult the audience. It just has to do with the fact that so this is, again, there's 4 different f stars going on, but this f star is derived from that one. So you're just applying the other one. And this one is a group homomorphism by construction. And so then if you have f star of a sum, that would be the other f star of a sum, but that becomes the sum of the 2 individual f stars. So we do not even have to bother to check that. Now, as an exercise, you need to complete the proof that Hn also preserves the identity, and it preserves commutative diagrams. So hence, we have a functor from topological spaces into abelian groups. And this is a functor, so we have a functor for each non-negative integer. So we have infinitely many different functors, so every homology is a functor. So these are the things you have to check. You have to show that the identity is preserved and commutative diagrams are preserved. But the proofs are not difficult. You just have to carefully do what we just did, kind of go through it. There's nothing clever. It's very straightforward, but it's a good way to practice these definitions. And then that's really the main purpose of this lecture, that homology is a functor. So you have to understand what a functor is and understand that what that implies about homology. Let us conclude this lecture by saying that homology is a topological invariant. And what this means is, and this is the proposition, if x and y are homeomorphic spaces, then their homology groups are isomorphic groups. That's what we mean by a topological invariant. If the spaces are the same, and same here means in the sense of topology, then the fundamental groups are the same, and same here means in a sense of isomorphism. And the proof of this is actually quite nice. And what I would like you to appreciate about the proof that you're about to see is that this proof uses absolutely no topology and it uses absolutely no group theory. This is a purely categorical proof. So actually, the nice thing about this proof is that it will extend to many other cases throughout mathematics. So you would say that since x and y are homeomorphic, we can find continuous maps from x to y and from y to x so that the composition, this is going to be the identity on y, and this composition, this is going to be the identity on x. Because what does it mean to be a homeomorphism? Homeomorphism means there's a continuous bijection so that the inverse function is also a continuous map. If you want, you can call G to be F inverse, if that makes you feel better, but it really does not matter what you call it. It's just the idea here that matters. Now here's what we do next. Now we have the following commutative diagram. X goes into y goes back to x, and this is the identity map. So then, if we apply the homology functor, we get the induced homomorphism on groups into Hn of x, and this is I star. But now we're going to use the two properties that a functor satisfies. The two properties are that the identity morphism becomes the identity morphism, so this is just the identity morphism for those groups. And secondly, this diagram commutes. So this diagram commutes because F and G, they compose to the identity, so this diagram commutes. So thus, if you do F star composed with G star, you get the identity. A similar argument will show that if you do F star compose G star, you would also get the identity. Now this is the identity on the other group, of course. This is the identity on the homology of x. That would be the identity on the homology of y. But this is showing that these are inverses. So thus, we have two homomorphisms. One of them is F star, one of them is G star, which are inverses. Which means that this is a bijection, that's a bijection between two groups, and this is its inverse, that's the inverse homomorphism. So hence, Hn of x is isomorphic as a group to Hn of y. So that is the topological invariance of homology. And I want to show you like an interesting way this can be used. I want to mention the Poincare conjecture. We actually talked about the Poincare conjecture last semester. So those of you who took the first topology course, we've talked about this before. So the question is basically this. You're going to suppose that X is a three-dimensional manifold. So I assume you know what a manifold is, but if you do not know, we'll eventually reach it in the course. Is a three-dimensional manifold. We can assume that it's connected. And maybe if that bothers you, just say it's path connected. If it's not path connected, then it has path components, and then you work with the individual path components. And you also assume that it's compact. Compactness is a very natural math condition that arises. It often arises when you fill up the missing points in your space. So sometimes you have a space of a certain collection of things, and if you have like missing points, you put in what are known as points at infinity, and when you put them in, you end up creating a compact space. So these are very natural conditions. Manifolds are very common in mathematics. Path connectedness or connectedness, depending which one you prefer to say, these are very common because if it's not path connected, it has path components, and then you work on the path components. And compactness arises in some sense of completion when you have no missing points. So very natural conditions. So you're now asking the question, under these assumptions, then X, if X is simply connected, I guess it means that then there's no need to even include that there because simply connected will imply that, but that's okay. So if X is simply connected, then X is the three-dimensional sphere. And by equal to here, we mean homeomorphic, of course, to the three-dimensional sphere. So that's the question. That's the Poincare conjecture. If the space is simply connected, must it be a three-dimensional sphere? So this was the problem that was stated in 1906, and then it was solved, as you all know, in 2006. Actually, I think that's earlier, maybe I think 1904. And it got solved in 2006 by Perelman. That's the Poincare conjecture. You can also ask, is this result true for 2 dimensions? And the answer is yes. And for those of you who are interested, this is what we did in the previous topology course. And the way we proved it is the way it followed was we actually classified all 2-dimensional compact manifolds. We just classified all of them. We had a complete list. And from that complete list of all 2-dimensional manifolds, we were able to show that the only one in that list that was simply connected was the 2-dimensional sphere. So it is true for dimensions 2. It is not true. It is not true. Well, I guess it is true. I mean, it's true for silly reasons. It is also true. It is also true in the 1-dimensional case. So we're asking that. So the 2-dimensional case would say, is X homeomorphic to S2? And the 1-dimensional case will ask, is X homeomorphic to S1? The reason, it's kind of funny why it's true in the 1-dimensional case, because there is only one-dimensional manifold that's compact and path connected, and it is simply just S1. Okay, so it's true for actually vacuous reasons. So you're saying that if X is simply connected, then is it S1? Well, if there is no, like S1 is not simply connected, but the hypothesis of this conditional statement is false. So there is no simply connected 1-dimensional manifold with those conditions. So it is true for silly reasons, just based on the fact that all such manifolds are homeomorphic to S1. So it is true in dimension 1, it is true in dimension 2. Proving it's true in dimension 3 was the hard one, because actually these are difficult, by the way. Even though this seems like a very innocent result, that 1-dimensional manifolds must be S1, even though that seems like a very innocent result, it's not easy to prove. This one is even harder to prove for 2 dimensions, and it uses the classification theorem. There's a classification for all 2-dimensional manifolds. By the time you get to 3 dimensions, there is no classification theorem. One can even say that people are working on a classification theorem for 3-dimensional manifolds. And you can say that the Poincare conjecture was like the first step towards classification. It was asking whether, if it's simply connected, in some sense the simplest type of manifold, must it be the 3-dimensional sphere? And the difficulty, of course, in 3 dimensions is that we do not have a classification theorem. We do hope that maybe one day we will have such a classification theorem, but for now we do not have such classification. And so Perelman had to somehow figure this out without having a classification for such manifolds. But we now know that this is true. But what about 4 dimensions? What about 4 dimensions and higher? You can also go higher. And interestingly, this is going to be the answer. The answer is it is not true. And this is a very funny theme through mathematics, that for some strange reason, that by the time you reach dimension 4, strange things begin to happen. So usually it's dimension 3 or 4 where strange things happen, but that's just the way it is. There's like a very interesting theme throughout mathematics that it's almost as if dimension 3 is like the most interesting one. But anyway, it's not true. And the reason why it's not true, it's something that people knew from the very beginning. There are very, very easy, simple examples that show that to you. And here is an example. This is a counterexample. The counterexample is this. You take a 2-sphere and you take a product with another 2-sphere. And the thing that you get is not homeomorphic to S4. Now, this is not obvious because R2 cross R2 is homeomorphic to R4. So maybe it works the same thing with spheres, but it does not work like that with spheres. Maybe just to give you a very easy example, if you take a product of 2 circles, that's not homeomorphic to the 2-sphere. This is the 2-sphere, this is the torus, right? This is the torus, this is the 2-sphere. And this is going to be actually something very similar, that this is the 4-sphere, and that's a product of 2 spheres. This has dimension 4, because you're just adding these together. and this has dimension 4. But this is simply connected. It's simply connected because the two-dimensional sphere, both spheres, the two-dimensional spheres are simply connected individually. So it's not difficult to show that their product is going to be simply connected. So that would be a counterexample. And then you can do something similar with higher dimensions. If you're talking about like 5 dimensions, you can do S2, S3, and S5, and they will not be homeomorphic. So from dimension 4 and onwards, it is not true, and that's something people knew from the very beginning. So it's not something that people were surprised with. But it's the 3-dimensional case that posed a lot of difficulty, and the other challenge actually here is, how do you justify this? How do you actually justify that a product of two-dimensional spheres is topologically distinct from the 4-dimensional spheres? And basically what you do is you just compute homology. You compute the homology of the product of 2 spheres, you compute the homology of this, and you just compare the 2 homologies. And you can compute homology of different dimensions. You can compute the 0 homology, the 1 homology, and things like that, and then compare whether or not they're going to be different. And you actually had this on the homework. You had a homework where you had to triangulate the product of 2 spheres, and then use that triangulation to compute the homology using simplicial homology. And you will notice, well, we did not talk about the homology of the 4-dimensional sphere yet, but we'll talk about that very soon. But you will see when you do the computations that you are getting different groups. And because of that, this topological space would therefore be topologically distinct from that topological space. So that would be the way that you show it. Okay, so we'll finish here. That's sort of the main idea of what we wanted to say, that homology is a functor, and we'll continue on with the next lecture.